This is a video for AQA Further Pure Mathematics, Sequences and Series 1.3, when we're looking at the sum of the squares and some of the cubes, so sigma r squared and sigma r cube. Well, the formula for sigma r squared, first of all, given here without any proof, but there are several proofs that you can look at in your textbook, and indeed we'll be looking at the proof of this in mathematical induction, which is in a later video. So sigma r squared is given as the product of n plus 1 and 2n plus 1 divided by 6, so 1/6 n plus 1 2n plus 1. So once we've got the formula, then we can use it to calculate different sums. Here we've got the sum of the first 20 squares, so writing this out full, it would be equal to 1 squared plus 2 squared plus 3 squared, etc., all the way up to 20 squared. But we can use the formula which says that this will be equal to n plus 1, 2n plus 1 over 6, so where n here is equal to 20. So here we get 20 multiplied by 21 multiplied by 2 times 20 plus 1, so that's 41, and everything divided by 6. And if you calculate that, you get a value of 2,870. Right, I just want to now look at the sum of the cubes and spend a little bit of time trying to work out what the formula might be. So let's take it one at a time. When n is equal to 1, this of course is just equal to 1 cubed, which is 1. With n equal to 2, we get 1 cubed plus 2 cubed. Well, 2 cubed is 8, so that gives us a total of 9. N equal to 3, we get 1 cubed plus 2 cubed plus 3 cubed. Well, we know that 1 cubed plus 2 cubed is 9, 3 cubed is 27, so we get a total here of 36. And then when n is equal to 4, just finishing this one off, we get 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. 4 cubed is 64, so in total here we get 100. Now I'm not going to go any further with that, but you begin to see a pattern, I hope. And indeed, I hope you recognise these as being square numbers. So what are these? Well, this is 1 squared, this is 3 squared, this one here is 6 squared, and then 10 squared. So hopefully you'll recognise that pattern, 1, 3, 6 and 10, as being the triangle numbers. And the triangle numbers were produced by the sum of r. So this is the sum of r from 1 to n, but all squared. Now a little bit more of that you can find in a GeoGebra file if you paste the reference that you have at the bottom of the screen. So what we've shown there then is that the sum of the cubes is the same as the sum of the integers are all squared. Now we know that the sum of the integers is n multiplied by n plus 1 over 2, so we're taking that and squaring it, which can be written as n squared and then n plus 1 all squared over 4. Now again then, that wasn't exactly a proof. It's a justification for the formula maybe, but if you want a proof you'll have some in your textbooks, and also we'll be looking at it in the section on mathematical induction. Well, once we've got the formula then we can use it to do some calculations. Here we've got the sum of the cubes from 1 cubed all the way up to 10 cubed. So n equal to 10, we can substitute that into our formula, so we get n squared, 10 squared, multiplied by n plus 1, so 11 squared, and then divided by 4. And if you calculate that, you get 3025. Well, that's the end of this video. In the next one, we'll be looking at using the standard formula that we've developed in the last two videos to find results of rather more complex formulae.